Welcome. We are discussing biomolecules and their relationship to the cell structure and function. We saw in the last lecture the microorganisms, and to see that we had a storyline. We were looking at why instruments are sterilized before a surgical procedure, and we asked a few questions, and we came down to bacteria which can cause infection, which is one of the things that can cause infection. And there are so many different bacteria in the world, in life, and so large that and so fundamentally different from other varieties that we call that a domain. Life, we said, had three domains: bacteria, archaea and eukarya, which are different in some fundamental ways, and these are called domains. There are many kingdoms in a domain, there are many phyla in a kingdom, there are many classes in a phylum, there are many orders in a class, and there are many families in an order, and there are many genuses in a family and many species in a genus. This is the taxonomy, as it is called, or the way organisms are classified, so that there is no confusion. Hopefully, you have gone through the videos here. We had mentioned that you could ignore some of these biological terms. They are just being, you can kind of get used to it without really knowing what they are. We will know most of the important things as a part of this course. You do not have to worry about that. So, you could ignore the terms such as RNA, DNA and so on and so forth at this stage, and watch this, and watch about let us say 2/3 of this video. I had talked about mnemonic to remember this. Do koalas prefer, I said, cheese or fruit? I think the video says chocolate or fruit, generally speaking. That is a mnemonic to remember this. And then we said that life is made up of cells, either single cells such as in archaea, bacteria, and some part of eukarya called protists and so on, or they could be made up of multiple cells such as fungi, animals, plants and so on. I said humans are made up of about 10^14 cells. And basically there are two types of cells, prokaryotes before nucleus and the ones with a true nucleus. We saw how they looked and their sizes and so on, and we also said that cell is the fundamental functional unit of life. If we understand this, then we have probably understood life, and we are nowhere close to this. And then we talked about organisms and so on and so forth, and I told you how a lab is sterilized, how that can also be used to sterilize operation theatres in hospitals, and there are other means, other more safer means of sterilizing operation theatres and instruments. Then we talked of bioreactors. Bioreactors are the production vessels. In fact, a bioreactor is a vessel, any vessel in which bioproducts are made, and there are so many bioproducts of use as we speak, and there are many more potential bioproducts being developed. I had given you a video for single use bioreactor and an image link for a large bioreactor. Bioreactors can be very large depending on their application. And then I told you a bioprocess, which is what is actually used to produce bioproducts. Bioreactor is an important aspect of it. And then we said that cells are subjected to shear in a bioreactor. This is going to be our second story. Our first story was about infection and so on and so forth. We learnt that organisms cause infection and what organisms there are, how they are classified and so on. So, our second story starts with shear in the bioreactor. Okay. This term shear itself could be new even to engineers who are students. If you have done probably a degree in engineering, you would know what shear is, or related fields you would know what shear is. Let us start from the very basis, and then I will tell you what shear is. That way we are all in the same plane. Let us consider a ball of chapati dough. okay, and place the chapati dough, puri chapati dough, in between the palms of your hands. Place your palms in opposite direction. I think I have kind of given the various steps here. Slightly press these palms and move the palms in opposite directions. When you do that, what happens to the ball? The ball distorts. It is chapati dough, okay, flexible, it distorts. The ball distorts due to the shear forces exerted by our palms when they are moved in opposite directions. Okay. The ball distorts when, because of what are called shear forces that are applied on the surface. These are exerted by the palms when they are moved in opposite directions. Okay. In other words, if you have some background in physics, you would understand this a little more easily. When there is a relative velocity between the two palms with the dough ball caught in between, then it results in shear stress or shear effects, as you can call, right. So, this is a requirement for shear to arise, that there has to be a relative motion, which means one part of the dough ball, in this case the upper part, needs to be experiencing a velocity that is different from the other end of the dough ball, let us say, and therefore, there is a relative velocity between the two ends, and if that happens, there is a shear force that is experienced by the dough ball. Okay. In a fluid environment such as a bioreactor is a vessel in which bioproducts are made by cells. The vessel is typically stirred to keep the cells in suspension. It could be operated in many ways and so on, let us not get into that. So, if it is stirred, there is going to be a lot of velocities and speeds in different directions, different velocities of the fluid particles in the bioreactor, and such an environment is very rife for a lot of shear forces to act. So, in a fluid environment as in a bioreactor, relative velocities or velocity gradients exist in abundance, which can cause shear effects on cells. Now, instead of a dough ball, let us consider a steel ball of the same size between the palms. And what happens to the steel ball when we move the palms in the opposite direction? Pretty much nothing, right? It does not distort, in other words. Why? Because the microscopic structure of the steel ball is very different from that of the dough ball. We all know that dough is made up of something which you will probably be able to guess as a part of this course, and steel ball is made up of steel. It is made up of steel molecules, or iron plus other combination and so on and so forth. And the microscopic structure of steel is very different from that of the dough ball, and with the shear forces that one is able to exert just by moving the palms in opposite directions, nothing happens to the steel ball. Therefore, it is important to know the microscopic or the submicroscopic components, because they are the determinants of the various properties of materials, right. This you would all be familiar with, different backgrounds, you would all be familiar with this concept, that it is the microscopic structure or the submicroscopic structure and components and their properties that determine the properties of materials as a whole. Now, let us ask the question, what gets affected by shear in the cells? Okay, let us say we know nothing about cells. We have been talking of various terms, I am sure even in the other lectures by Dr. Madhulika Dixit, she would have mentioned a lot of terms. We will clarify all the required ones in this as a part of this course at different points in time. You do not have to worry about that. So, what gets affected by shear in cells? The first guess would be the envelope that covers the cells, right. That is a very rational guess. So, what does the cell envelope contain? The cell envelope may contain what is called a cell wall and a cell membrane. Remember, these two are different things. One is called a cell wall, the other one is called a cell membrane, and both of them envelop the cell, right. The cell wall and the cell membrane both are found in some bacteria, in plant cells and so on, or the cell wall could be completely absent. Okay. Only the cell membrane distinguishes the cell from its surroundings, right. And that is the case with all our cells. All animal cells do not have a cell wall. They just have a cell membrane, and that is what is exposed to the environment. Typical cell wall is about 20 nanometers thick. Okay. You can imagine the size, meter, then centimeter is 10 power minus 2 meter, millimeter is 10 power minus 3, micro is 10 power minus 6, nano is 10 power minus 9. Okay. This is 20 nanometers thick, is rigid, and therefore contributes to maintain the cell structure such as integrity, rigidity, shape and so on and so forth. That is typically what a cell wall does. You could look at this particular link here. By the way, I think this is the right time to show you the various links. I did mention a file, a PDF file that would have these links that can be clicked. I think control and a click would take you there. Let me show you that file. I think this is the right time to show you that. Right. This would be available as a part of your resources. I think it is available right below or right above. I think there is a link, a button on the right hand side of the video when you play them, and if you click that, it will take you to this file. So, these are sources, many of which are required and some of which are optional. I will point out which are optional. If I do not say it is optional, it is required, okay, required to appreciate the course better. As I mentioned, we cannot play these videos here, therefore, we have given you the links so that you can go and take a look at them. The videos have been chosen for their didactic value, for their value to teach. IIT Madras and the instructors of this course, both Madhulika and I, may not endorse the other views that are expressed in the video or the products that are featured in the videos. Some of these very nice videos have been made by companies to sell their products, but we do not endorse the products. So, we have seen all these videos designed through mimicry. I did not mention the second one, but please go through it. It is a very nice short video from the Science magazine about a cockroach based robot. This is in the introductory lecture, and these were the various biomimicry lectures, and then the artificial retina lecture, brain computer interface lecture, and then the 3 domains of life, biological classification, single use bioreactor. These 3 were videos, and the large bioreactor is an image, and the cell wall number 11 is what we are talking about right now. Okay. If you click on this, you will get an image that you could see. Let us get back. And the cell wall is predominantly made up of 2 kinds of molecules called peptidoglycan and teichoic acids. Okay. Just the terms, I am just going to float this around, do not worry about the terms as of now. If it is important enough, we will go and see what it is. If it is not, just hear the terms, so that if you hear the terms later, you will at least vaguely remember, and I have kind of heard this somewhere. That is good enough. And if it is important enough, then you would be repeatedly exposed to it and you can pick it up. The plasma membrane, the earlier we talked of the cell membrane, the cell wall. Now, let us talk of the cell membrane or the plasma membrane. This is where it is very interesting. How does the cell membrane look like in a microscopic sense? It looks something like this. This is a 2-dimensional structure. This is shown as some sort of rectangular, a cuboidal kind of a structure. This is a cell, right? You take a small part of the cell, it will look like this, and if you extend it in all directions and assume that it is covering some sort of let us say a spherical shape or an oval shape, then you can understand how this fits into the structure of the cell, right. So, you have the cell membrane consisting of 2 layers, as you could see. The first layer is this circle here and some of these squishes, the lines here. the second layer is circled here and the other lines in the opposite direction, right. So, in other words, it has a double layer here. It so happens that the nature of this is very different from the nature of the ball is very different from the nature of these lines here. We will come to that. In addition, there are a few other things. There are these green things that are shown and there are these blue things that are shown. We will get to that. The green things are actually proteins. We will see what proteins are, although we have heard the term so many times, we will see what those proteins are, and these are carbohydrates that stick onto it. We will see what they are. Okay. For now, let us focus on this double layer here, which has if you take one molecule that comprises the double layer, it has this round head and a certain tail. Okay. So, Sanger and Nicholson described the structure of a cell membrane as some kind of a fluid mosaic. Mosaic is just made these things put it together. So, this is a mosaic of what are called lipids. In fact, these molecules that we have been describing so much here, these are called lipids, and there are proteins and there could be other things also. So, Sanger and Nicholson described the structure as a fluid mosaic of lipids, which are these, and proteins, which are seen here. That is good enough for now. Okay, that is what a cell membrane is. Therefore, shear can quite easily tear the membrane apart, because they are all floating around. Okay, you provide enough surface force, the shear is going to tear apart these lipids. And some cells, such as I mentioned, the mammalian cells, our cells, do not have a cell wall, and the plasma membrane is directly exposed to the environment, and therefore, they are much more shear sensitive than when compared to the cells that have a cell wall. Okay, this is common sense. When you use these cells in the bioreactor, mammalian cells are used in the bioreactor for production of high value products such as monoclonal antibodies, which are used for cancer therapy and so on. And when these cells are used in the bioreactor for production of these, they are directly exposed to the various stresses because of the velocity gradients in the bioreactor, and those shear stresses can break the cells apart. Okay. So, what are these? Let us look at the nature of this molecule. It is an important class of molecules. Definition is very vague, okay, and that is the best that we can get, and let us start with the vaguest definition in biology pretty much. Lipids are water insoluble molecules which are very highly soluble in organic solvents such as chloroform. Okay. I know it is vague, but let us stick to it. That is what a lipid is, and that is one of the 4 major classes of basic biomolecules that are present in life. Okay. So, for example, you all let us take this molecule here. Okay. This is a 3 carbon molecule. Okay. If you know a bit of chemistry, you would know this is glycerol, the one that is shown in yellow or some shade of yellow there is glycerol. It has 3 OH groups here, 3 carbons here, and to one of these OH groups a long chain carbon molecule with a COOH gets attached. Okay. When this gets attached, the H2O gets out and the C joins with this O. So, you have a CO on the other side, this O on the other side, and this bond going on to this O to provide an example of a lipid. Okay. So, you have a fatty acid which is hydrophobic, and you have a glycerol which is hydrophilic, and you attach, you could in principle get a lipid. So, this has I think 18, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 palmitic acid, C16 is a palmitic acid, and all these bonds in between these carbon molecules are all single bonds. Okay. Therefore, this is a saturated fatty acid. So, saturated fatty acid with glycerol is an example of a lipid. Now, instead of one fatty acid attached to one of this OH, what was initially OH of the glycerol, If you have 3 fatty acids attached to the 3 oxygens of the glycerol through ester linkages as they are called, then you get fat, right. All the fat that that causes a lot of social difficulty is nothing but this. Okay. It is a triglyceride. You have 3 fatty acids attached to a glycerol molecule, and that is your fat. Fat is a lipid. So, fat causes whatever difficulties and all that is a lipid. It is called a triglyceride, okay, because you have a glycerol, you have a glyceride bonds being formed here for 3 fatty acids, and you have a triglyceride there. C18 stearic acid is nothing but butter. Okay. It is saturated. If it is saturated, you get butter, and C18 with a single double bond gives you oil. Butter saturated because all the bonds between carbon atoms are single bonds, and here one bond is a double bond, which actually introduces a kink in the structure, and you have fatty acid with one bond unsaturation, and then you get oil. Okay. You know how useful these products are, and this is the molecular nature of these products. C18 is butter, C18 with a double bond is oil, unsaturated oil, and so on. Okay. All these saturated, unsaturated terms that are used by doctors actually refer to the nature of the bonds between the carbon atoms. So, this is the 3-dimensional view. Let us just focus on some parts of it. There are many parts to it which let us not worry about. So, this is the double layer plasma membrane. As I said, it covers the cell. This is a part of the plasma membrane. Assume that it is extending in various directions, and you see how it can cover the cell. So, this plasma membrane has a double layer of lipids with a lot of proteins sticking around, a fluid mosaic of lipids and proteins, and then there are various other things which we will not worry about now. Okay. If you are interested, you could see this video by clicking. I think it is video number 12, the item number 12 here, plasma membrane. You could see this, and that will improve your appreciation of the plasma membrane. So, let us go a little deeper. Let us try to understand this a little better. So, I am taking a part of the plasma membrane, a 2-dimensional view. So, this is the bilayer of lipids. You have the hydrophilic heads here. Hydrophilic just means water loving, and therefore, when it is exposed to water, it will tend to orient itself towards water, and you have these hydrophobic tails. In other words, this is a part, this could be a part of the glycerol molecule, and this could be the various fatty acids. Okay. Typically, there are 2 fatty acids here, and this is what has been blown up here, right. These are the fatty acids. This is probably saturated, this is probably unsaturated, and you have some other molecules here which are hydrophilic, they like water, and these are hydrophobic molecules, and this is a structure of one of this pair blown up, okay, nothing else. Phospholipids, glycolipids, and cholesterol are the major types of lipids that occur in a natural membrane. Okay. In other words, we saw the triglyceride, right, the glycerol molecule being converted into triglycerides. That was an example. In the phospholipids, this is different, as we will see later. There is another set of molecules called glycolipids, where this part is different, and cholesterol, which is completely different molecule. We will see that in a little while. Okay. Cholesterol is a very commonly known molecule. It was supposed to cause a lot of difficulty. People have the American Heart Association has changed its view on cholesterol now, but it is popular anyway. So, it will be nice to see what it is all about. Okay. So, this is a phospholipid, particularly phosphatidylcholine. These are the fatty acid chains, the hydrophobic it should be hydrophobic here, hydrophobic tails that are here, and this is the glycerol molecule. As you can see here, the 3 carbon chain here, and 2 of those O molecules are attached to the fatty acid. The third molecule of O is attached to a phosphate group, PO4 minus group, and then there is a choline group that is on top of that. Okay. This is called phosphatidylcholine. As you can see, this is a hydrophilic end and this is a hydrophobic tail. So, this fits into the various needs of a lipid, and this is an important constituent of natural membranes. This is cholesterol, right. You see all this here, all this is the hydrophobic part and this OH is the hydrophilic part. Okay. And the cholesterol is also a lipid that doctors thought caused so many problems earlier. Okay. How do lipids in the membrane determine shear sensitivity? How sensitive the shear is? Okay. There are various types of lipids. So, depending on the types of lipids that are present, the shear sensitivity should vary, okay, because the properties of the constituents determine the overall properties of the whole, right. So, let us see how that is, and let us see an application of that towards our needs. For that, let us consider 2 lipid bilayers. The first bilayer is made up of phosphoglycerides containing only stearic acid, okay, C18. C18 saturated, and the other is made up of phosphoglycerides containing oleic and stearic acids. Oleic, as you know, has 1 unsaturation, stearic has no unsaturation. Because of that, if both are stearic, okay, this is the hydrophobic tail, hydrophilic head, if both are saturated, such as stearic acid, the structure is going to be something like this. Whereas, if it is 1 oleic and 1 stearic, the stearic is going to be straight, the oleic is going to have a kink, and therefore, it is going to occupy more space compared to stearic here. Okay. And therefore, if we tightly pack lipids containing both stearic acids, it is going to pack something like this, okay, reasonably tightly packed. I am just showing one layer for clarity. You can imagine the other layer on the other side. Whereas, if we have both stearic and oleic present on the phosphoglycerides, then it is going to pack like this. The area that is the space that is occupied by each of this is going to be higher. Therefore, the packing itself is going to be much less dense than the one with both stearic acids, and therefore, the membrane fluidity is going to be high due to the loose packing, whereas here the membrane fluidity is going to be low due to the tight packing. So, it is quite easy to see that the tightly packed thing is going to resist shear much more than the loosely packed thing. A smaller amount of shear force can tear this apart compared to this. Okay. So, that is very simply how the structure of the cell membrane determines its shear sensitivity, and the structure of the lipids or the constituents, the nature of the constituents determine the structure of the membrane, and the structure determines its property. For example, membrane fluidity. Loosely packed structure will be more shear sensitive. Okay. Suppose we think of making the cells more robust to shear. Okay. Shear is our story here. Suppose we think of making the cells more robust to shear. What do? We need to understand, of course, more about membranes and how are membranes made in the cell and so on and so forth, what are the functions of the various components, and then somehow make the cell to make or to generate the kind of lipids that we need to have a more densely packed membrane, and therefore, more shear sensitive cell lines or mammalian cells maybe, okay, if you are going to use them in the bioreactor, right. So, this is one way of thinking about it. Fine. I think we will stop here for this lecture. We will continue further when we meet next. Very briefly, in this lecture, our story was about was about shear. We saw what shear was. Let me quickly go back to what we saw. We saw what shear was. I told you in some detail what shear was, and that it can cause damage to cells, especially in an environment such as a bioreactor environment, which is full of shear. And the microscopic or the submicroscopic components need to be known because they determine the properties of materials. And then we asked the question, what gets affected by shear in cells, and we came up with our first guess, a cell envelope, which consists of a cell wall and a cell membrane. We very briefly looked at the cell wall, and then we looked at the cell membrane in some detail. We saw that it was a fluid mosaic of lipids and proteins, and we saw what are lipids, which I said was one of the 4 major classes of biomolecules, and they are defined as lipids are defined as water insoluble molecules which are very highly soluble in organic solvents such as chloroform. And then we saw a few examples. Our fats are actually lipids, and then butter is a lipid, oil is a lipid, and then we looked at some of the details of phospholipids and cholesterol, and there is another type, glycolipids, and all these 3 are commonly found in natural cell membranes. Then we saw how the membrane characteristics determine membrane shear sensitivity, and we also looked at a case where we could possibly modify the lipids to modify the shear sensitivity. Let us meet again later, and when we meet again we will continue with another story. See you then.